Hi, I'm Mr. Evans, and today we're going to build off the force diagrams we've been drawing to solve for, well, to continue to solve for mass, to solve for net force, and to solve for acceleration. And so with that being said, let's real quickly throw a net force onto our board. And I'm not going to label every single arrow because I have very limited space. But let's say we have 500 this way, 600 this way, 600 down, and 300 to the left. Okay, what you do when you solve for net force is consider your up and down arrows as one plane and your left and right arrows as another plane. And so with that being said, the up and down arrows are 600 minus 600, and the left and right arrows are 500 minus 300. And so with that being said, our net force is 200 to the right. Okay, because our up and down canceled out, and so that's 0, so it doesn't matter. Our left and right did not cancel out. There's 200 left over with the bigger number to the right, and so our net force is 200 to the right. So let's do another one real quick, and let's say we do have two different net forces, and so we do our up and down, which is 200 minus 100, and we do our left to right, which is 10 minus 0, that 0 being that there is no arrow on the left side. So with that being said, our net force is currently 100 up and 10 to the right. And so this would be our final net force for now. Eventually, I'm going to have you reapply our a squared plus b squared equals c squared, but we will talk about that in class. But essentially, keep in mind that the up and down is, one of these, while the left and right is the other one, and you could solve for the actual net force. So the reason this is important is because with net force we can solve for mass, we can solve for acceleration. And so our equation we're going to be working on today is F equals ma, with m being mass, and mass is in kilograms, and a being acceleration, which is meters per second squared, F being newtons. And so you can always solve for one if you have the other two. And so if we have our box over here, and we have 50, 50, 50, and 25, and our mass is 3 kilograms, I can solve for the acceleration of the object. I can say the up and down arrows are 50 minus 50. I can say the left and right arrows are 50 minus 25. So our net force is 25. So I can plug that in for F, which is in newtons. Our mass is 3, and I can solve for A now. And so if you divide both sides by 3, our acceleration is 8.3 meters a second squared. This same process can be used to also solve for mass. And so if I have an object in here and I give you its net force, which let's just say it's 50 to the right, let's say there's nothing opposing it, which is pretty unrealistic, but just for the sake of space. So we have F equals ma. I give you net force, and I tell you that this object has an acceleration of 5 meters per second squared. So with that information, we can go back up to our problem, or our equation, and say our force is 50, which is net force again, don't just add up the forces, equals mass times acceleration, which is 5. So then we can solve for mass, and our mass of this object is 10 kilograms. So I think where this can sometimes get a little tricky is when you're solving for actual force or an arrow. And so let's do one more example in here before we wrap up this video. And let's say I have a box here, And as always, we have gravity. Let's make it 150 this time. 150 up. Oh, 150 up. And let's say there's 25 friction force and some unknown force here. And we have a 6 kilogram object that's moving 3 meters per second squared. Well, it's accelerating. Okay, and so we need to solve for this force here. So we start by just plugging these into our equation. Like always, we know acceleration, we know mass, so let's solve for force. So F equals mass times acceleration. So F equals 18 newtons. This is where people tend to mess up, is they just want to plug that 18 in. The issue is this is net force. And so that means our net force has to be 18 newtons to the right. And so with that being the case, our x over here has to actually be 18 more than 25, right? And so net force in our left to the right has to be something minus 25 equals 18. And so x, our actual net force there, is 43 newtons. Keep in mind this is kind of an introductory level of questions, and so we could do one, and we'll do one as quickly as I can possibly draw, where you have a force this way and a force up. And so, you know, let's just pretend there's nothing here, which is again probably pretty unrealistic. And so, you know, if the object is 4 kilograms and I want to know its acceleration, you would first have to find net force, and so we have 25 to the right, and and 10 up, and so we'd have to do our a squared plus b squared equals c squared. So we have 25 squared plus 10 squared equals c squared, and so if we solve for c, we get, so c equals 27 newtons. And so our actual net force is 27 to an angle, right? And so with that being the case, now we can do 27 equals 4 times a. And so a, or our acceleration, equals 6.75 meters a second squared. So hopefully this is helpful, and from here we'll move forward in a different video, don't worry, to how to use this information to solve for a velocity after a certain amount of time, and even moving from there into kinetic energy.